Hello my wisdom freaks, today we will talk about thermodynamics and statistical mechanics. Thermodynamics and statistical mechanics are branches of physics that deal with the behavior of systems composed of many particles, such as atoms and molecules. They provide a framework for understanding the macroscopic properties of matter in terms of the microscopic behavior of its constituents. Let's break down the concepts and their interplay in detail. Thermodynamics. Laws of thermodynamics. 1. First law, conservation of energy, stating that energy cannot be created or destroyed, only transformed from one form to another. 2. Second law, entropy tends to increase in isolated systems, representing the directionality of processes and the emergence of irreversibility. 3. Third law, as the temperature of a system approaches absolute zero, its entropy approaches a minimum value. Thermodynamic variables. 1. Temperature, T, measure of the average kinetic energy of particles in a system. 2. Pressure, P, force exerted per unit area by particles colliding with the walls of the container. The volume V, space occupied by the system. 4. Internal energy, U, sum of the kinetic and potential energies of the particles in the system. Thermodynamic processes. Isothermal, occur at constant temperature. Adiabatic, no heat exchange with the surroundings. Isobaric, occur at constant pressure. Isochoric, isometric, occur at constant volume. Thermodynamic equilibrium. Thermal equilibrium, system and surroundings are at the same temperature. Mechanical equilibrium, no unbalanced forces within the system. Phase equilibrium, coexistence of multiple phases in equilibrium, e.g. solid-liquid equilibrium. Statistical mechanics, microstates and macrostates. Microstate, a specific arrangement of the particles in a system characterized by positions and momenta. Macrostate describes the system in terms of macroscopic variables like temperature, pressure, and volume. Boltzmann distribution describes the distribution of particles among energy levels in a system at thermal equilibrium. Higher energy states are less populated than lower energy states, following the exponential relation given by Boltzmann factor. Entropy and statistical mechanics. Entropy is related to the number of microstates consistent with a given macrostate. 2. Boltzmann's entropy formula, Saklonos Carnot, where SS is entropy, Kk is Boltzmann's constant, and OO is the number of microstates. Partition function. 1. A function that summarizes all the possible states of a system. 2. It is used to calculate thermodynamic properties such as internal energy, free energy, and entropy. Ensembles. Microcanonical ensemble, isolated system with fixed energy, volume, and particle number. Canonical ensemble, system in thermal equilibrium with a heat bath at constant temperature. Grand canonical ensemble, system in thermal and diffusive equilibrium with a reservoir at constant temperature and chemical potential. Phase transitions, changes in the macroscopic properties of a system due to a change in external conditions like temperature or pressure. Examples include melting, freezing, vaporization, and condensation. Connection between thermodynamics and statistical mechanics. Statistical mechanics provides a microscopic foundation for thermodynamics by explaining macroscopic properties in terms of the behavior of individual particles. Thermodynamics provides the framework for understanding and predicting macroscopic phenomena based on empirical observations and principles, while statistical mechanics provides the underlying microscopic explanation. Both approaches are complementary. Thermodynamics deals with macroscopic quantities and laws that govern them, while statistical mechanics deals with the microscopic behavior of particles and their statistical properties. In summary, while thermodynamics describes the macroscopic behavior of systems in terms of a few measurable quantities, statistical mechanics delves into the microscopic details of particle interactions to explain the observed macroscopic behavior. Together, they form a powerful framework for understanding the physical properties of matter at different scales. I hope you liked this video. Don't forget to like and subscribe.